Welcome guys. Welcome guys sa first lesson natin sa finals. Bali continuation to no ng graphs no nung last part ng ating lesson sa semi-finals o pre-finals no. So may mga terminology dito na na-discuss natin before no nung last part ng ating semi-finals. So mga definition na lang yung ating didiscussing dito no. Okay? So again, definition ng graph. A graph is basically summarizes how many quantity changes if another quantity that is related to it also changes. Okay? So for example, itong ating graph, meron tayong implementation ito sa isang mapa, sa isang geographical location, no? So kapag in-implement natin to sa isang geographical location, kung merong label yung kanyang edges, ang tawag dito ay weighted graph, no? Kung meron namang arrow, yan, katulad ng discussion natin before, that would be a directed graph, no? But in this case, wala tayong arrow, so this is an undirected graph. Pero meron siyang label, so representing the distances between the towns, okay? So considered siya as weighted, no? Weighted undirected graph. Okay? So marami tayong pwedeng implement or usage no sa graph. Pwede itong mag-represent ng underground tunnel network or a network pipes, okay? Representing the pipe diameters in its edges, no, as a label, or a railway map. And also we indicate the flights to or ferries or also with political alliances, no? So mayroon akong papakita sa inyo example kung saan ginagamit na application ang graphs, no? So ito yung pathfinder na flight tracker. Ito. Okay? So ayan, no? Ito isang application, no? Ito ay web apps, no? Ayan. Kung saan makikita natin yung currently, no, online, real time, no, ano yung mga eroplanong kasulukuyang nasa flight, no. So katulad nito, punta tayo sa bansa natin, Philippines, yan. Makikita nyo maraming naipong eroplano nanggagaling sa Manila. Okay? Yan. So pag sinom natin yan, makikita natin dyan yung kanilang movement. Okay? And these movements represents the path of the graph, no? So this application uses graphs, and the nodes, okay, are represented by each airplanes, no? So yung from location 1 to location 2 also represent the nodes, no? And the plane represents the direction by which the edges are tracking, no? So tulad ng airplane na to, no? So makita natin ito ay galing sa Manila, HYT flight HYT 9080, no? Hindi lang natin kung saan to papunta. Okay? So bigla siyang nag-turn right dito. Okay? Yun na siya. Makikita nyo online siya, no? So this one is using this application is using graphs as its main database structure. Okay? Kabalik tayo sa lesson, no? Maganda rin panoorin to pag minsan, lalo na pag meron kang kamag-anak na umalis, currently nasa airplane niya. Okay? So dito na tayo sa lesson. So there's much more that can be done with such a picture of situation than just reading of which place is directly connected with another place. For example, we can ask ourselves whether there is a way of getting from A to B at all, or what is the shortest path, no? So ito yung tinatackle sa traveling salesman problem, no, which is solved by a graph. Okay? So ano yung ibig sabihin ng traveling salesman problem? Involves finding the shortest route through the structure that visits each city precisely once. So kung ikaw daw ay salesman at marami kang tao na dapat puntahan para makabenta ka, para hindi daw masayang yung iyong oras, dapat ano yung path na pwede mong daanan kung saan hindi ka nababalik. Ibig sabihin, kung pag nadaanan mo na isang path, hindi mo na dapat siya balikan pa or daanan uli. Okay? So this is solved by implementing the graph theory. Okay? So we go now with graph terminology, which is discussed already from the previous lessons. No? The kind of structure in Java figure is known as formally as a graph. A graph consists of a nodes, vertices or points, and edges, which is also called lines, links, or the directed graphs or arcs. No? Displayed as connections between the nodes. There exists quite a lot of terminology that allows us to specify graphs precisely. So we have different type of graphs. We have simple graph, which says it has no self loops or circle, no? So kapag sinabing simple, wala dapat circle graph, circle path, no? Yung isang graph na merong isang edge na merong single vertex, no? And then we have also, if there are labels on the edges, yan, we say that the graph is weighted. We distinguish between directed and directed graphs in a directed graphs. Okay? So this is the example of the directed graphs. There are no labels of its edges, so it is not weighted, no? Again, this is an example of a weighted directed graphs because there are labels on its edges. In undirected graphs, we assume that every edge can be viewed as going both ways. No? That is, an edge between A and B goes from A to B. So kapag wala daw arrow, we can consider, no, na yung direction ng edges niya ay works both ways. No? So pwedeng from A to B or B to A. No? The first graph given at the beginning of this chapter is weighted and undirected. Okay, so the path is a sequence of nodes or vertices such that BI and BI or vertices plus 1 are connected by an edge for all, which is not greater than the last edge. Note that in a directed graph, the edge from B1 to BI plus 1 is the one which has the corresponding direction. A circle is a non-empty path whose first vertex is the same as its last vertex. So, umikot lang kasi siya. So, yan yung sinasabi nating loop, no? May self-loop. A path is simple if no vertex appears on it twice. So, kung walang circle, simple yon, no? With the exception of a circle where the first and last vertex may be the same. An undirected graph is connected if every pair of vertices has path connecting them. So, kung every vertices daw ay connected, then that is a connected undirected graph. For directed graphs, the notion of connectedness has two distinct versions. We say that a digraph is weakly connected. Ito under to ng directed graph, okay? It can be weakly connected or strongly connected. Pag sinabing weakly connected, if for every vertices A and B there is either a path from A to B or path from B to A, we say it is strongly connected if there are paths leading both ways. So, sa directed graph, kapag double arrow, then they are strongly connected. Kung single arrow lang, then they are weakly connected. A graph clearly has many properties similar to a tree, but a tree can be viewed as a simple graph for a particular kind, namely one that is connected and contains no circle, no? So, pag simple graph, sabi natin, no circle. Pag tree, wala ring circle and it has only one direction, no? Because a graph, unlike tree, does not come with natural starting point. So, yun ang isa pang difference ng dalawa, no? A tree kasi is a kind of graph, but a graph is not necessarily a kind of tree, no? So, ang graph kasi walang starting point. Ang tree meron, yung tinatawag nating root vertex, no? From which there is a unique path to each vertex. It does make sense to speak of parents and the children in a graph. So pag graph, hindi natin ginagamit yung salitang parents or children, no? Kasi sa tree lang natin pwedeng gamitin yun kasi meron siyang hierarchy. Instead of two vertices A and B are connected by an edge E, we say that they are neighbors. So neighbors lang ang pwede nating itawag sa dalawang magkatabing vertices, no? And the edge connecting them is said to be incident to A and B. Two edges that have vertex in common, no? So, kung meron tayong edge na nakakonect sa isang vertex, which is the circle, then ibig sabihin nun ay they have vertex in common. And then if they have vertex in common, then they are said to be adjacent. Okay? Implementing graphs. So, paano yung sinasabing implementation? We need to use it by inserting, deleting, searching, and sorting the collected items. At no time there were any connection between all the items represented apart from the order in which their keys appeared. No? So yung mga previous example natin, walang connection concern, no, dun sa mga instruction na diniscuss natin before. But right now, in implementation of graphs, we are focused on the connection. No? So it is the connection that are the crucial information we need to encode in the data structure. We are given structure which comes with specified connections, and we need to design an implementation that efficiently keeps track of them. Okay? Ang one implementation natin is yung array base. Okay? So, alam natin kung ano yung array, di ba? So, the first underlying idea for array-based implementation is that we can conveniently rename the vertices of the graph so that they are labeled by a non-negative integer indices, say from 0 to 1. So, katulad ng discussion natin before, ito yung kanyang, ito mga number dito, yung kanyang weight, no? Yung kanyang label ng edge. Ito naman yung vertices. So, kapag 0, ibig sabihin itong A to A, walang loop, so walang edge. Si B, 0 din. At paano yung may edge? Ibig sabihin yung A to B, may edge, so magka-connect sila, no? Si A to B. Si AC, wala. AD, meron. So, they are adjacent because they have the same vertex, no? Si AB and then si AD. Okay? So on and so forth. Pag ang value ay 0, then they have no edges. Kapag merong 1, then they have edges and they are connected. Dito naman sa merong infinite loop, ito yung represent dito yung directed graph. This is a representation of undirected graph. Okay? So, ang problema dito sa array base is kapag marami na tayong malaki yung ating graph, then it would be illogical and not advisable to use the array based implementation, no? So, anong gagawin? Anong solution natin? The solution is sorry. The solution to this problem is to number all the vertices as before, but rather than using a two-dimensional array, we use a one-dimensional array that points to a linked list of neighbors. So, mixed implementation ang tawag dito kasi gumagamit tayo ng array base sa loob ng gumagamit tayo ng linked list structure sa loob ng isang one-dimensional array. Okay? So, for example, ito. So, we have yung mga arrow na yan represents the list or the link connecting the linked nodes. Ito, mga nodes to. Okay? But, sabi rito, there's still a problem with this implementation is using the so-called adjacency list. Note that if you're considering undirected graphs, there is still a certain amount of redundancy in this representation. No? Kasi merong nauulit na mga connection, no? Connected vertices. So to solve that, we use the pointer-based implementation. The standard pointer-based implementation of binary trees, which is essentially generalization of linked lists, can be generalized for graphs. In a language such as Java, class graph might have the following as an internal class. So ito yung present lang natin yung object, no? Object niya is vertex, then ito yung mga properties niya. So we use that as the structure for the pointer-based implementation. Okay? So kapag daw gumamit tayo ng pointer base, then the structure will be like this, no? Instead of using so much storage, no, na hindi naman kailangan kasi mayroong redundancy na ulit na connections, we have the pointer base implementation. So notice nakokonti lang yung ating nodes or vertices na maire-represent, no? Ibig sabihin niyan, kukonting space lang makakain, no? If ever gumamit tayo ng pointer-based implementation. So, relationship with graphs. Many important theorems about graphs rely on formal definition of relations between them. So, we now define the main relevant concepts. Two graphs are said to be isomorphic if they contain the same number of vertices with the same pattern of adjacency, no? So, magkakalapit, pareho ng distance, pareho ng pattern, pareho ng number of vertices, then they are isomorphic. A subgraph of a there is a bijection between the vertices which preserves the adjacency relations. So pag sinabing bijection, yung isang vertex may dalawang edges, no, na nagko-connect sa dalawa pang vertices. That is called bijection. A subgraph of a graph G is defined as any graph that has vertex set which is a subset of the G, which is defined as any graph which has G as a subgraph. So kapag daw, for example, itong sub G as itong graph G at yung another graph H, then if they are isomorphic, then we can consider that the H is a minor of the graph G when they have the same number of the same structure, no? For example, they have a simple path, and we have the G has a simple path and the H has a simple path also. Then H is considered as a minor of subgraph G. Okay. Subdivisions of graph G can be defined as graphs resulting from subdivision of the edges in G. So yung subdivision, ibig sabihin yung edge dito natanggal. So nagkaroon tayo ng unconnected two graphs, no? So an edge contraction removes an edge from a graph and merges the two vertices previously connected by it. So yung edge contraction daw removes an edge from a graph and merges the two vertices previously connected by it. This can be lead to multiple edges between a pair of vertices or self-loops connecting a vertex to itself. So kapag pinag-iwalay daw, there is a possibility na magkaroon ng edges na nagkakaroon ng self-loop, no? For example, si vertex V, yan, magkaroon ng edge pabalik sa sarili niya. Okay? And that is called edge contraction, no? Yung pagtanggal, pag-alis ng edges at pag-merge ng dalawang graph. Traversals, we already discussed this, but this will be the final discussion for there are other examples for the breathe in or the breathe first or the depth first traversal, no? So let's go now with the two types. Let's go with breadth first traversal. We start with a given vertex side, then we visit its neighbors one by one, which may be possible no matter which implementation we use, placing them in initial empty queue. So remember, pag sa breadth first traversal, we use the queue structure, no? We then remove the first vertex from the queue and one by one put its neighbors at the end of the queue. So pag sinabi natin queue, ang ano niya horizontal, no? Kaya nga breadth first, okay, papaganon siya. Okay? So pumapasok sa uli, lumalabas sa unahan. Okay? So we then visit the next vertex in the queue and again puts its neighbors at the end of the queue. Okay? So kapag daw ganun nangyari, there's a possibility na hindi ma-terminate yung implementation or yung traversal. Ibig sabihin magkaroon ng infinite loop, no? Kasi pumapasok pa rin dun yung mga na-visit na, no? Dun sa queue. So para maiwasan yon, however, there is no reason why this basically should ever terminate, no? So maaring di daw mag-terminate yun at magkaroon ng infinite loop. So ang gagawin daw dyan is to avoid this, we can create a second array done at ang pangalan ng array ay done of booleans where done j is true if you have already visited the vertex with number j. So papalitan lang natin status nung mga vertex na na-visit na, no? Parang tatatakan na nung array, no? Na siya ay na-visit na para hindi magkaroon ng infinite loop. So kapag na-visit na, ay tatak na siya na done, ay hindi na siya uli mababasa nung system. Now we go now with the depth first. Bakit depth first to? Given a vertex I to start from, we now put it on a stack, no? Rather one that done was put on the stack, then we take it from the stack, mark it as done. As for breadth first traversal, look up its neighbors one after the other and put them into the stack. So pag depth first, pababa naman siya, no? So we use the stack, no? So lumalabas lumalabas sa unahan, lumalabas din sa unahan, no? Kasi ang stack ay iisa lang ang kanyang access point. Okay? So dun siya pumapasok, dun din siya lumalabas. So hanggang sa maubos niya yung nasa ilalim. So yun yung sinasabing depth first, no? So imagine pag breadth first, papaganito siya. Okay? ang basa, ang pag-visit niya ng mga vertices. Kapag naman depth first, yan, inuuna niya yung mga nasa baba. Pababa, taas ulit, pababa, taas, pababa. Okay? And that is the end of our lesson 1 for our finals.